Hello, hello, hello. Welcome to EduTechie for another time. And today we are going to do one more problem. The name of the problem is climbing stairs. Now imagine you're standing at the bottom of a staircase, right? You can climb either one step or two steps at one point of time. Sounds simple, right? But this problem has tripped up thousands of developers and estates across the industry, especially when they get this during a coding interview. Because what happens is, like most people, straight away jump into the code, but when, as an interviewer, I have been taking interviews at thousands of places. As an interviewer, we aren't testing your syntax in this. We are testing your thought process, right? So in this video, I'm going to break down the climbing stairs problem from scratch with a visual representation, understand the hidden patterns behind it, and then try to implement both the solutions. So first I'll try and implement it with a brute force solution, which will be a recursion and backtracking solution. And then I'll try to optimize the solution and show you step by step how you can actually optimize the solution. And for the brute force solution, I'm also going to show you why that fails. Right? By the end of the video, you will not only solve this problem confidently, but you will also be able to explain it in a granular fashion during any of the interviews that you're going to face. Right? So without wasting any further more time, let us get started. Let me share my screen very quickly. I hope my screen is completely visible to all of us. And this. I've tried to actually visually represent the entire problem, try to break down the problem. So what happens? As I already said, right? At any given point of time, we are allowed to climb any one step, or we are climbing two steps at a time, right? So I have tried to break down this problem with starting from, we are standing at the ground floor where, like, we don't have any other floors above it. And for that, when n equals, we are considering that to be n equals 0. So for n equals 0, we can say that the number of ways we can climb is straight away 1. It's 1, right? For n equals 1, what are the number of ways? Because we have just first floor and ground floor. So from ground floor to first floor, we have only one possibility, that is we can climb one staircase, right? So the number of ways we can climb is 1. From ground floor to second floor, now according to the problem, we are allowed to climb one step at a time or two steps at one time. That is what I've written, right? One step at a time, 1 comma 1, and two steps at one time, so 2, right? So there are two possible ways to go from ground floor to second floor. Now when n equal to 3, ground floor to third floor, what are the possible ways of climbing? We can climb one step at a time, which is first floor, second floor, third floor, or what we can do, we can climb one step at a time and then two steps, or we can directly climb two steps at one point of time and then followed by a single step. For n equal to 4, what happens? There are 5 possible ways to get that. So what are the possible ways? We can climb one step at a time, 1 comma 1 comma 1 comma 1. Or else what we can do, we can climb one step, then followed by two steps, then one step. Or we can start with two steps followed by one step and one step. Or what we can do is we can climb one step followed by another step and then take two steps. Or the final way that we can climb to the fourth floor is, like, we can take two steps and then we can take two steps, right? So I hope the problem statement is completely clear, right, to all of us. Now, looking at the problem, what essentially are we doing? We are essentially trying to, let's say we stand at the second floor, right? How can we reach to the third floor? How many possible ways we can reach to the third floor? So we can write that W3 is nothing but W2 plus W1. That means the number of possible ways that we can climb the first floor plus the number of ways we can climb the second floor should be equal to the number of ways we can climb the third floor. So we can simply write here that W3 should nothing but be equal to W2 plus W1. Similarly, if we come here and see, what is W4? W4 is nothing but, if you see, the number of possible ways we can climb to the third floor plus the number of possible ways you can climb to the second floor, which is 2. Number of possible ways to climb to the second floor is 2, as indicated in this diagram, and number of possible ways to climb to the third floor is 3. Right? So what is number of possible ways to climb to the fourth floor? Is nothing but 2 plus 3, which gives us 5. And this is how I have broken it down as well, right? So if you try to break it down, every possible way you can climb, these are the possible ways, and you can see this 1, 2, 3, 4, 5, right? So it matches. how can we climb the first floor? And let's say like when we are at the ground floor, there are no floors below ground floor, right? So we can automatically say that if n is less than 0, that means anything less than the ground floor, there will be no possible ways to climb any staircase because there are no staircases at all, right? That's it. That's the problem statement. And now we will see that what is the brute force solution, what is the brute force approach to this problem, and how we can solve this problem. So let's jump onto the brute force solution. So as you can see that this is a recursion tree, right? This is a recursion tree. How we have drawn this recursion tree? So if you imagine that this is the number of ways to climb to the fourth staircase or fourth floor, what we do here is uh, like we are basically adding up the number of ways it will take us to climb to the second staircase plus the number of ways it will take us to climb to the third staircase. So it's a binary tree because at each node we are having two branches, right? One is a left branch and another is a right branch, and the outcome of the left branch and the right branch, when we add them up, it actually gives us the node above it, right? The parent node or the root node for these two leaf nodes, right? Again, if I consider W3, the number of ways to climb to the third staircase, it's nothing but W2 plus W1, right? What is W2? W2 is W1 plus W0, and W1 is W0, W minus 1. And what is W0? As I already told you that it's going to be mathematically or diagrammatically, it's going to be W of minus 1 and W of minus 2. But actually, there will be no W of minus 1 and W of minus 2, right? Because there are no staircases below the ground, below the last staircase or the ground staircase, right? So that we can consider automatically as 0. So anything less than 0 is all W of anything less than 0 is always 0, and W of 0 is of course 1, right? W of 0 is of course 1. So how do we start this? So let's consider that W of 0 is 1 because I showed you in the previous diagram, right? The number of ways that we can when we are standing at the ground staircase, then there are no possible ways apart from one way, right? We will be standing there only. So there's only one way. What is W of minus 1? Anything less than 0 is 0, of course, right? So we have the value of W0 and W1, right? And this is our base case of the recursion. So now what we try to evaluate, we start from the top node W4, right? We see, okay, it's W3 plus W2. Now we try to again go down the left branch. So what is the left branch? It is W3. Again W3 we go down, W2 W1, right? Again W2 we go down, W1 W0, right? Again we go down, W1 is W0 W minus 1. So W0 and W minus 1 we have. W0 is 1, W of minus 1 is 0. So add them up, it's 1, right? So we have the value of W1, which is 1. Now what is W0? Again we know that W0 is nothing but we are returning 1 here. So W1 is also 1, W0 is also 1. Again, if we try to evaluate W2, we simply backtrack, W1 and W0, and W2 will actually give us 1 plus 1, which is 2, right? Again, we go to W3. What is W3? It is W2, which already we have got as 2, right? And we try to evaluate the value of the right node. Now we come down this right branch of W3, right, which is W1. W1 is again subdivided into W0 and W minus 1. What is W0? This is 1. W of minus 1 is 0. So 1 plus 0 is 1. So this W1 is 1. We backtrack W1. So when we evaluate W3, we come to W2, W1, and we backtrack these values. So this is W2 is 2. W1 is 1. So 2 plus 1 is 3. So W3 is 3. So now when we try to evaluate W4, we actually do W3 plus W2. So to get W2, W3 we've already got, right? What is W3? W2, which is 2 plus W1, which is 1. So 2 plus 1 is 3. So W3 we've already got as 3. Now how do we get W2? Again, we have to entirely go down this particular right branch till the end and start evaluating. So let's evaluate this. What is W0 and W minus 1? W0 is 1, W minus 1 is 0. So this value gives us 1 plus 0 is 1. So W1 is 1. What is W0? W is 1. So there's no need to evaluate W1 and W minus 2 in this case, right? So because W0 we can already backtrack and we can see that this is already evaluated to 1 because we are returning 1 from here. So there is no point, right? Again, when we return, so these branches actually don't make any sense, right? Because W0 we are already returning it as 1. So there's no point in drawing these branches out. So my mistake, this branches will actually is not required. So W0 is 1, W1 we already evaluated as 1, which is W0 where we return 1, W minus 1 we return 0. So 1 plus 0 is 1. So here we get W1 as 1, W0 as 1, and 1 plus 1 is again 2, which is equal to W2. We already evaluated W3 as 3, W2 is now 2. So again, W4, we backtrack W3 and W2, so 3 plus 2 is 5, and that's the answer of our recursion, right? So you imagine that to get W4, how many nodes we had to traverse for this left child and this right child, and how many times did we traverse the nodes and did we backtrack, right, to get the values of the previous nodes. And you see that we are also doing some redundant calculations in both our left sub branch and our right sub branch, right? So that's the problem of recursion. What is going to be the time complexity of this code? Since every node has only two possible branches, and we have n number of levels where n equal to 4 here, so the time complexity of this code will be 2 raised to the power of n. 2 raised to the power of n, right? So without wasting further more time, what I'm going to do is I'm going to simply code the solution up, and then I'm going to show you that why this solution is so efficient. As I already told that we are doing redundant work here when we are trying to call this recursion tree stack, and we are doing a lot of redundant work, right? And the time complexity is also much higher, on the higher side, right? It's 2 to the power n. So it's an exponential sort of time complexity, right? My code editor here. So what do? We are taking n equal to 3. Let's take n equal to 4 because that's what we showed in the diagram, right? And what we are going to do here, we're going to say that if n is equals to 0, we simply return 1. That's where we stop. We don't have any more child nodes, right? We don't have any more child nodes. Or if n is less than 0, what we are going to do here is we are simply going to return 0, because diagrammatically or visually we can definitely represent these nodes, but actually in an actual scenario there is no staircase below ground staircase, right? So we don't have any staircase in an actual real life scenario. So we are saying that there are no ways to climb any staircase because there are no staircases at all. So we return 0 if the value of n is anything less than 0, right? And now what we try to return is, we say that we are returning evaluate. We'll simply recursively call this function, and what we are doing n minus 1 plus evaluate, and this will be n minus 2, because when we are at when we are evaluating W4, we are essentially evaluating W3 and W2, right? And I showed you how we drew the recursion tree and how we were backtracking, right, when we were evaluating those values, right? And these two are our base case. These two are base cases. Like if n equals 0, that's where we stop. We don't traverse any more nodes because there are no more nodes. We simply return 1. If n is less than 0, we return 0. Now, if I run this particular code, you see what happens. So what should be the value? The value should be 5. That's what we evaluated. So we get that the number of distinct ways to climb is 5. So let me try and increase the font size here. So you see that this is the code. This is the code. This is what we are doing, right? I already explained the code. I don't think so that we need any more explanation, right? So this is the recursive code. Now let us try to understand the problem. So let's try to increase the value of n, right? Let's make it 10. Let's see what time does it take. I already told you what is the time complexity. Time complexity is 2 to the power n, but let's see it visually, right? Let's see this. Let's run this. See, it's fast. It's fast, right? So let's go. Let's make n equals 20. Let's see. All right, it's still fast. Let's make n equals 30 and see. Let's try with an increasing number, right? All right, it's fast. It's fast. So let's make n is equals 40. Let's see the time complexity of this code. Okay. It was a bit slower. It was a bit slower as compared to n equals 30, right? You must have observed this, right? Let's make n equals 50. Let's see now. Let's see how much time we need. All right. So you see that this is the drawback of this code, right? Now you have to wait and wait until you get the output. And when you see this video, I'm not going to clip this part off from the video because I want you to see visually that what happens. Because when n is a large number, you imagine that recursive tree that you have, right? The number of leaf nodes that it will have and the number of redundant recursive calls that it needs to make and the number of times it needs to backtrack, right, to get those values in the tree stack, right? So that's the problem. See, it takes ages. It takes ages. This code, this particular solution simply blows up for a large value of n. It simply blows up, and that's why it's not a recommended solution. You imagine you are actually doing a client facing, you're writing this code for a client facing application, and your API takes ages to give the response, right? What will happen at the front end, right? What will happen at the front end? The user will just run away. The user is going to run away. You see that we are talking for such a long time, but still we haven't got any values. We still haven't got the output. And now that we get the output, so imagine that this is the response time of an API. We are already screwed, right? So without wasting further more time, we are going to see that how we can improve this code, right? We're going to see that how we can improve this code. So how can we improve this particular solution? How can we improve this particular solution, right? So we are essentially what we are doing. We can, instead of having those different nodes, those leaf nodes that we are evaluating, right? So for every, why this is taking time? Let's try to understand why this is taking time. It is taking time because now my root node is 50. When I'm trying to evaluate W of 50, that is actually trying to do that recursive call, and it is trying to go to the end of the tree where it is finding the base case, and then it is backtracking the values and evaluating the parent nodes one after the other, and it is reaching to the root node, which is like n equals 50, right? So that takes a lot of time because there is a right sub branch, there is a left sub branch. So there are two sub branches at which it needs to evaluate. Imagine if we would have cached the solution, right? If we can cache the values, so every time we give, let's say we give n equals 2, if we can cache the value of n equals 2, and if we can use that value to evaluate n equals 3, then it's going to be a much faster response, right? So imagine for n equals 50, we have already cached the values of W49 and W48. We don't even need to go down the recursive tree and do all those redundant backtracking, right? So in that case, it's going to be a much faster solution. So here we actually implement the solution of caching, which is nothing but dynamic programming, right? So we'll have a cached array. So what can we say? Let me remove this code and see how we can modify this code, how we can optimize this code, right? So let's first let's take an array, right? So let's say long ways to climb is equals to new long, and here we can say n plus 1. Why n plus 1? Because we were starting from the ground node. You remember, we're starting from the ground node, which is n equals to 0, right? So if n equals 4, we are actually essentially calculating n equals to 0 to 4, right? That's what we are doing. So we are taking n plus 1, right? Now what we can store here? So this is our cached array. This is where we are caching the values, right? So we say that this is nothing. What is the number of ways to climb? Zero steps. That means there's only ground floor, right? There's only ground staircase, nothing. So that's 1, right? We already saw that it was 1, right? What is the number of ways to climb the first staircase? Of course, it will be nothing more than 1, right? Because that you only have one staircase to climb to, right? So the option of two, like climbing two staircases at a time, doesn't even come into the picture. So we can say 1. So now what we do, we start our loop, and from, let's say, I is equals to 2, and then we go straight away till n, and we do I plus plus, and here we say at every time when we calculate the value of ways to climb of I, we are caching the value. We are storing the values in this ways to climb lookup array or the caching array, right? So we'll say that ways to climb of I will be nothing but equal to ways to climb of I minus 1 plus ways to climb of I minus 2, and that's it. So that's it. And what we return? We simply need to return the ways to climb 50 staircase. So in this case, it's 50, right? That's where it blew up, the previous recursive solution. So we just say it's in. So now if I run this particular code, you see that how drastically this time complexity improves. See. It happened in the blink of an eye. Why? Because every time we are evaluating the ways to climb of I, we are essentially caching the previous two values, right? When we started from 2, the 0 and 1, these two values were cached. When we are going to 3, we are already having 2 here in this particular array, right? So 2 and 1 is already present. So all the values will be cached for any value of n. The n minus 1th and the n minus 2th value is going to be cached, and it will not take much time to access those values, unlike the previous recursive solution. So now we are going to write the time complexity and the space complexity down. So let's start with the recursive solution. So for the recursive solution, uh, what was our time complexity? The time complexity of this particular code was 2 raised to the power of n, where n is the number of uh, n are the number of stairs, or the number of levels are the number of levels. So that's better way to say it. Number of levels. And what was the space complexity over there? The space complexity was O of 1, because we were not taking, it's not O of 1 because we are taking so many spaces in the memory, right? So again, it'll be simply equal to the number of nodes that we are occupying in the memory space. So I will say that this is going to be O of n, where n, or O of m, where m is nothing but the number of nodes we are occupying. And that's definitely the number of nodes that we are occupying is 2 to the power n only. So we can say m is 2 to the power n, nothing but 2 to the power n only, right? So now what is the time complexity of the improved solution, or the dynamic programming solution, right? What is the time complexity of that particular solution? The time complexity of this particular solution is simply O of n, because time complexity is O of n. It's a linear solution. It's not an exponential solution, unlike the other one, because in this case we are using a cached array, and we are caching the values of n minus 1 and n minus 2 at every step, right? So this is O of n. We just need one for loop to run it. That's it. I hope you liked this particular solution. It's an extremely important problem from the from the thought process, how a person is thinking during an interview process. And trust me, these are asked in multiple FAANG companies. So if you like this video, and if you appreciate me going through the different solutions and the visual representations of the solutions, please do like, comment, and subscribe. Watch this particular video till the end, because it's going to be a short and very important video. And this is going to be a very good starting point to understand recursion backtracking as well as dynamic programming. With this, I'm going to stop sharing my screen, and I'm going to stop the recording as well. Thank you, everyone.